When you write complex asynchronous JavaScript using raw promises, your code tends to drift sideways. You chain one dot then inside another, attach a catch, and quickly end up with a nested, hard-to-read structure known as the Pyramid of Doom. To reduce that cognitive load, we need to straighten it out. JavaScript implements async await as Syntactic Sugar, a clean, structural wrapper sitting directly on top of the standard promise engine you already use. When you use the await keyword, it expects a promise. It waits for that promise to settle, extracts the fulfilled value directly from the operation, and cleanly assigns it to a variable on the left side of your equation. Looking at this clean, top-to-bottom code, it creates an illusion that the program has stopped to wait. But await only pauses the local function's execution. It immediately yields control back to the event loop, allowing the rest of your application to remain interactive while the network does its work. Transforming nested callbacks into linear logic shifts your focus from managing indentation levels to tracking the actual sequence of your application data. But this clean syntax introduces an immediate vulnerability. In a raw promise chain, you handle network failures by chaining a .catch method at the end. Without that method, where do the errors go? If a network request fails, a rejected await promise throws a hidden synchronous style exception. If left unhandled, that exception halts the function's execution entirely, stopping the rest of your logic dead in tracks. To protect your application, you must explicitly wrap your await operations inside a standard try-catch block. If the network drops, the execution safely falls into the catch block instead of breaking the app. This pattern unites your error handling. You can now catch standard synchronous logic bugs and asynchronous network failures in the exact same execution block, using conditional logic to filter between local type errors and remote server issues. Treating async await code as strictly synchronous without the safety net invites silent application crashes into your production environment. This sequence diagram illustrates the chronological downward flow of time between a browser and a server during a single fetch request. Now imagine an application that needs two pieces of data to load, a user profile and the global high scores. If you write two await statements sequentially, you create a waterfall trap. The engine forces the first request to finish completely before the second request begins. If each takes 2 seconds, your user waits 4 seconds total. Look at that empty, idle space. Do these requests actually depend on each other? The high scores don't require the user's profile data to begin fetching. Running them in sequence wastes time. To bypass the waterfall, we use Promise.all. We group our independent network requests into an array and pass that entire array to a single await statement. The engine now executes them concurrently. The second request slides over to start at the exact same time as the first, dropping the total execution time down to 2 seconds. Writing clean code is only half the job. You have an architectural responsibility to recognize whether your data has serialized dependencies, or if it can be optimized for parallel execution. Let's apply this to a production-grade scenario. We are building a dashboard that requires the user to authenticate first, and then immediately fetch their messages and notifications at the same time, with a fallback if the UI fails to load. We start with an async wrapper and lay down try-catch guardrails. We await the login process, then deploy Promise.all to fetch notifications in parallel. This establishes a reliable blueprint, extracting values with await, securing execution with try-catch, and maximizing speed with Promise.all. These specific patterns routinely appear in technical interviews because they demonstrate that you can balance clean, readable state management with highly optimized front-end performance. Migrating away from raw, nested callbacks to a structured async pattern elevates your work. You move past simply forcing the code to compile and start engineering a resilient, high-speed experience for the user.